All right, we have some fabulous speakers tonight. Our main speakers are Danila Marini and Dr. Danila Marini and Dr. William Billingsley. Danila will be talking about virtual fencing technology and its use on farms, while William's going to give us an insight into how computer technology is learning to understand us. A bit more on that later. First of all, we're going to hear from our rapid-fire science speakers. Pay close attention to their names and their talks, as we have an iPad to give away to the audience favourite, which is calculated over the 3 nights of Pint of Science, as well as some of their talks are going to be included in the trivia a bit later on. And further to that, we'll be hosting a Q&A session at the end of the evening where you'll be able to ask questions of any of our presenters tonight. So let's get started. Our first rapid-fire speaker is Mafroz Basoni, and he's going to talk to us about the roles of the plant hormone auxin in rice endosperm development. Where's Mafroz? Ah, here he comes.
Hello, good evening, everyone. My name is Mafroz Basunia. I am going to present my research in 5 minutes, which will be very difficult to do. I'll try my best. So I'm going to talk to you about the roles of plant hormone auxin in rice endosperm development. But first the question, does rice plant grow in Australia? Let's have a look. Yes, it does. So rice grows in this Murray-Darling basin. So yeah, in this region. And in fact, it's the third largest cereal crop in Australia. So it means a lot of money for Australia. So now the next question. What is rice endosperm? It is in fact the grain that we buy from supermarket and cook and eat. So the white area there, this is the rice endosperm. And the endosperm stores different kinds of nutrients like starch, protein, some vitamins. So the endosperm consists of 2 layers, alluron layer and the starchy endosperm. So here is the alluron layer, this single layer, and then the white stuff inside is the starchy endosperm. So my research is mainly concerned about alluron layer. So it's a bit big slides, but we just need to know some key dates in the development of rice endosperm. So these are rice flowers, and they get pollinated by wind. And after being pollinated, these rice flowers are developed into grain. And the alluron development is complete by 9 days after pollination. And then from 5 to 21 days after pollination, that starchy endosperm development is complete. So my research is concerned about the role of a particular plant hormone called auxin, or indole-3 acetic acid, chemically. So we would like to know the roles of this auxin during endosperm development. So the auxin levels in rice endosperm is very high. Here, if you look at this figure, leaf, root, endosperm. So endosperm contains the highest amount of auxin found anywhere in rice seed. So in the endosperm, there are 2 endosperm-specific genes called UCA. So one is OS-UC11 and OS-UC12. These 2 genes make auxin in rice endosperm. And these 2 genes have also their counterparts in other cereals. And for my research, this information is very important. So OSU12, it is expressed together with another two genes, OSIA29 and OSMRP1. We reckon that these two genes are involved in auxin signaling. So my research is basically concerned about these three genes. So far, we know that rice endosperm has the highest level of auxins found anywhere in rice plant, but we basically don't know what auxin is doing during the endosperm development. So my research will be to find some answer. And so this is my aim of the study, what is auxin doing during endosperm development in rice. And my hypothesis is that auxin signaling is regulating the aleuron development. You remember that aleuron layer, that single layer around the starchy endosperm. We think that this layer development of this layer has something to do with auxin signaling. Why? Because the OSYAC12 is expressed just during the aleuron development, and it is expressed with these three important genes. And auxin can control the expression of all these three genes. So I'll test my hypothesis by a number of techniques. So just so far, qRT-PCR is done, and waiting for the other things to complete. So my study, theoretically, it will contribute something about roles of auxin during endosperm development, and practically, it may contribute to create resilient rice varieties, especially for Australian environment. That's all. Sorry. Sorry, I did. Yeah, that's all. Thank you.
Thanks very much. Thanks, Mavroz. Our next rapid-fire speaker is Iman Theta-Jaw, and she's going to talk to us about the determinants of Environmental Awareness Index and pesticide demand of tomato farmers in Inler Lake.
Good evening, everyone. My name is Iman Theta-Jaw. I come from Myanmar. I'm a PhD student. And this is my previous research of my master thesis. The titles of my research is Determinants of Environmental Awareness Index and Pesticide Demands of the Tomato Farmers in Inle Lake. Inle Lake is situated in my country. Why I do this research? Inle Lake is the second largest inland lake in Myanmar. It was situated in southern states of the Myanmar. And the watershed area of Inle Lake is about 39 kilometers square and 7.69 kilometers in length and 6.43 kilometers in width. This is the Inle Lake. Inle Lake is famous for the ecotourism services. Many of the ethnic peoples in here are doing ecotourism services and agriculture. This is the floating currents in Inle Lake. Floating currents is the famous and attractive place in the Inle Lake. Many of the in the peoples are growing. A lot of vegetables and flowers are growing on the floating current. I would like to explain how to make the floating current. Firstly, they kept the white grass along the lake, and then they throw in the white grass to the desired place, and then they are anchored this white grass by bamboo poles, and after that it is covered by the silt from the lake. And then they grow in a lot of vegetables and flowers on the floating currents around the year. Tomato is the major crops in this area. And in recent decades, the inland lake was faced a lot of environmental degradation process. In the summer season, they face a lot of the drought problem. And another problem is the water pollution. And because of the heavy utilizations of the pesticides and herbicides in floating current cultivation. And the next one is there's 4 bug and 5 members of the species are threatened in extinction condition. And moreover, the waters in lake are not drinkable anymore because of the water pollution. According to the NILA 2012, the main causes of water pollution is the floating current cultivation. So I would like to do this research the following objective. But according to the limitations of the time, I would like to present only the objective, one of objectives. This is to investigate the environmental awareness index and determinants of environmental awareness index of slated tomato farmer. I was conducted the service and interviewing method to collect the data. I collected the 107 farmers from the 7 villages in here. This is the questionnaire for the to determine the environmental awareness index. I calculate the environmental awareness index by using this equation. This is the linear regression model to determine the determinants of the environmental awareness index. Let's move to the research and discussion. According to the research, there are 5 groups of the environmental awareness index are obtained from this calculation. As you can see that 47% of the farmers gave the 0.78 to 0.87 environmental awareness index. This means many of the farmers know the harmful effects of the pesticides and insecticides and they have a highly environmental awareness index. From the results of the regression model and the age of the farmers, the family size of the farmers, and the pesticide experience of the farmers are significantly different at 1% level. It means that the farmer who has a higher age, older ages, and smaller family size and smaller pesticide experience farmer has more environmental awareness index. So, in conclusion, farmers notice the pesticide harmful effects. However, they have not willingness to reduce the pesticide uses because of their livelihood security. And lack of the formal pesticide training is the major problems of the farmers in this lake. So I would like to recommend like this. Research and development programs are needed to progress the pest and disease-resistant tomato variety, and then trainings and education programs are needed for the farmers, and public health education is very critical thing for the farmers. So the government should, and then the government should monitoring the pesticide companies in their formulation, packaging, and promotion, and good agriculture practice, and integrated pest management systems and the conservation of deforestation is essentially needed for the conservation of this area. In addition, farmer environmental awareness would be the major driving force for the environmental conservation in this lake. Therefore, the policy drives of environmental awareness will be very important for the future livelihood. That's all of my presentation. Thank you very much for your kind attention.
Thank you very much. All right, we have one final rapid fire speaker. That's Min Pockrell, who's asking the very interesting question, how the introduced and native dung beetles are faring in the paddocks.
Looks like very cold today. Good evening, everyone. I'm Min Pockrell. Actually, I'm working on very fascinating, handsome creatures. Most of you may be familiar with. Why fascinating means these are getting equal attention since ancient civilization to modern scientists. We can learn in ancient Egypt, those beetles were actually enjoying very sacred status as a god Khepra. And for the present scientists, they are still point of attraction because of their capacity to navigate the Milky Ways and multifunctional ecological services. So in this regard, I have selected this beetle for my research. Actually, one more interesting thing we can correlate with dung beetles is, first time in the history, the number of car cell, that means newborn car cell, is greater to that of newborn babies. That's very interesting fact. What does that mean? That means increasing living standard and growing economies of many countries. Ultimately, that demands more nutritious food, especially the animal products. We know that meat and dairy products. That's lovely for everyone. So, in this case, the role of dung beetle is a bit increased because they have to bury more dung because of the increased livestock production globally. So, the importance, again, high of those handsome beetles. Actually, the beetles are providing very important, that means environmental functions, ecological functions. We know they are recycling nutrients and water, the best to the farmers. And in Australian context, they control pestiferous flies, bush flies, and many livestock parasites and diseases. Furthermore, they enhance actually grass growth by improving soil properties, and they also disperse grass seeds. And some other important role like pollination are still unleashed. So the value of dung beetle is estimated to be multi-million dollar in different countries. US has estimated $380 million per annum per year, and similarly 367 million pound in UK. That means very high economic role in Australia is to be estimated. So we know this continent is like a homeland of roos, kangaroos, wallabies, wallaroos. And after the introduction of those cattle and sheep, the role of native dung beetle was something different, because the native dung beetles were co-evolved with marsupials and some other small mammals. And the native beetles, those are very high in number, nearly 500. 437 are described well. Those beetles could not handle the juicy, wet, and very big cow dung pad. So Australia has introduced some international beetles, like we people. So after the introduction, after nearly this 240 years of cattle and sheep introduction to this continent, and nearly 45 years of overseas beetle introduction, my research question is how the endemic abundant, that means 437 native beetles and 23 introduced beetles are working together in paddocks. That was my research question. So to address my research question, actually, I have selected some sites just to see what differs with elevations. For the purpose, I have selected 8 different sites from nearly 300 meters to 1,300 meters above the sea level. That is from Manila Terminus to Gaira it was lucky. I got many sites within a short distance. Though the site difference is, the distance between sites is nearly 87 k's plus minus 25. So regarding season, I have selected all the seasons, except winter. And for the habitats, both native and improved pasture land. And I am using actually both cattle and sheep poo and kangaroo poo, just to see my research question. I have mentioned you that I have selected those 8 sites, and I have set up 12 standard pitfall traps like this in each of the sites. In native grassland, I have set up such 6 standard pitfall traps, and in improved grassland paddock, similar 6 traps. And I have used 3 different types of dungs for the attraction of dung beetles. So we can see some native grassland and improved pastureland, and these are some of the glimpses of my field sites. The result is something interesting. For 2 seasons, I have collected 11,000 beetles of 25 species. Very interestingly, out of those 437 native and 23 introduced beetles, we see 77% of the beetles and then 68% of the species are introduced. That means introduced beetles are a bit abundant and mostly dominant. And summer was the most abundant season, followed by spring and autumn. In summer, we got big number of beetles. And regarding the elevation, actually mid-elevation was a bit good for beetles because we got more number of beetles in mid-elevations. I have selected 300 meters to 1,300 meters above the sea level, but this height is optimal for the beetle abundance. Regarding the pasture land, actually I could not see any differences. In native and improved pasture, the number of beetles looks to be the same. Regarding their actually richness, species abundance, some species are really abundant in one season and not in the other. We can see first species, Untitled fulvus, was abundant in autumn, but we could see that is like 4th ranking beetle. And regarding this Apodius fumitorius, we cannot see any more in that autumn season. So the beetle species are different with the season. Their abundance is very different. Regarding the attractiveness of dung, very interestingly, sheep poo was more attractive as compared to cow and kangaroo poo in total. But again, the introduced beetle are more attracted to cow poo as compared to sheep and kangaroo poo. That's also something cool result. And very interesting one is, we can see the native beetles are more attracted to sheep poo as compared to that of kangaroo and cow poo, but I cannot say it is significant or not. Something interesting, because sheep poo may be similar to that of kangaroo poo in shape or size, and maybe more nutritious, less fibrous, so more native beetles are attracted to sheep poo. Some challenges over in my research actually still are that demands very high physical labor. I have to do all the time. 96 pitfall traps, we have to dig in all the time, probably we have to dig it again. So kangaroo poo, arranging kangaroo poo was also challenging, and sheep poo was also. And again, the deadly snakes, I was encountered actually a few times, even with my friends also. And ID of native beetles, actually no more keys and something like that for ID. I acknowledge my donors, Halsworth and UNE research grant. And the more farmers, they provided me access to their properties. And lab medicine volunteers, because after the encountering snakes, I could not go alone in the field. So thank you so much.
Thank you very much. Now, the rapid fire speakers are all in the running to win an iPad. So there's about 8 of them over the 3 nights. On your table, you will find an attractive ripped in half A4 piece of paper that has their names on it. So have a think about who your favourite speaker was. I personally find the fact that sheep poo is more attractive than kangaroo poo informative. So label your speakers there 1 to 3. While you're doing that, we're going to take a 10-minute break and then we'll be back with our main speakers. Grab yourself a pint. As well as being a postdoctoral fellow at the University of New England, Danila works at the CSIRO, focusing on behaviour and welfare of livestock and their learning capabilities. Please welcome Dr. Marini. You came from a different direction.
Thank you. And
Clicker.
exactly what I need. All right. Hi, everyone. So, yes, I am Danila, and I work with the University of New England, although I'm very decked out in CSIRO right now. So I'll be talking to you guys about virtual fencing. So I had this slide in here, so you guys saw that nice little video about CSIRO. Here's just a little bit more information about them. So how many people in this room actually knew CSIRO invented Wi-Fi? There we go. So some of you guys have learnt some new facts. We've also been involved with the creation of many interesting, exciting technologies, such as the one I'm talking about today. And that is managing sheep with invisible fences. And I should really say cattle, because this is where it started. But I'm a sheep person and very biased, so there's a lot of sheep in here. So Australian agriculture is continually advancing and improving. So our farmers in the field are at the top of their game, and they're constantly changing to meet the rapidly changing environment. So farmers have to face things such as pests that are in this environment. They have to change with they have to act with climate change, and also the fact that farms are now getting bigger and there's less farmers to work on them. So we have to help farmers be able to tend to their land. So we're helping with such as technologies to help manage pests, to improve crops and improve their production, as well as improving animal production and helping them become more resilient with this ever-changing environment that we're in. And all the meantime, we have to do this sustainably. So this really wordy slide is just some of the things that CSIRO does to help farmers meet this challenging environment that they're currently working with. And the one I'll be talking about is technology on farms. So we do a lot more than just virtual fencing. So how many people here have heard of drones or seen drones? A lot. So drones are one of the most common technologies. You can buy these things off the shelf, and they're very handy and useful for farmers. So this one here is a little CSIRO helicopter, and it actually can go over crops and detect pest plants within the crops. And these drones can be used for a variety of things. You can fit all kinds of cameras to them, such as infrared, and they can spot differences within your crops and can help you figure out where you need to put certain things, such as fertilizers within the soils. As in a giant paddock that we have in Australia, there can be vast differences from one end to the other. And this kind of technology can help farmers plan out how they can make better use of their farm. And there's also little things like this. So it doesn't look like much, but this is a wireless sensing technology that CSIRO uses. So this actually detects water salinity in the ground, and it can help the farmers manage just water usage, saving them money, time, and also water, which is a very valuable resource in this country. So they're really handy things that can be used on farm. And of course, some of you, if you're coming from UNE, have probably heard of pastures from space. So this actually uses satellites that are currently orbiting around the Earth constantly to actually get an accurate picture of your farm. So a farmer can pick a specific paddock within his farm, and he can actually detect the biomass. So that's actually the feed available on the ground to then make better choices as to how he's going to manage his cattle or sheep on that ground, so then he can make better use of his grass. And of course, we have more than that. We have these things for sheep as well, so it's not just, you know, all pastures and crops. So this thing over here is an Rfid ear tag. So they're, I don't know how many people have heard of RFIDs. Has anyone heard of them? A few. So RFIDs can actually, they pass through an electronic point that picks them up. So it kind of uses it as a tracker. And we use them to actually identify individual animals. So how farmers can use these RFIDs, so as I've got an example here, is we're scanning the animals as they're going through the race. So we can find the individuals that we know we have that are within this group. And then we can assign them to certain things based on us knowing who they are. They can also be used through certain systems, such as they're often used like at water points. So when sheep are traveling to go get some water and they're walking through them and they have lambs, it can be used to actually match up accurately a ewe with its lamb. So it can give farmers more accurate progeny records using this kind of technology. So what about virtual fencing? Isn't this meant to be what I'm talking about? So virtual fencing is one of these new types of technologies that farmers can actually use to help improve their farming. And it actually incorporates some of the technology that I've already mentioned. So how does it actually work? So first, it's been created for cattle, really. So what we do is we put this collar on a cow. So it's a smart collar that has a solar panel at the moment to keep it running indefinitely. And it also has GPS. So it talks to GPS satellites that roam the planet, just like pastures from space. And what the farmers have to do is they just use their computer program and they write down the GPS coordinates, or in this case, they can just draw the fence line that they want in their paddock. And this talks to a base station that they have on their farm, which then talks to the collar that the cow has. So those coordinates they've set up through GPS will put down this fence that we have here, and it'll keep the cow within that fence and using GPS. So how does the cow actually learn what a virtual fence is or how they can actually interact with it? So we'll take a step back. Virtual fencing kind of works a little bit similar to normal fencing, but it's a little bit smarter. So think about an average fence, like an actual electrical fence or something like that in a paddock. So an animal learns through this thing called associative learning. So the cow walks up to the fence. It's a conditioned stimulus. They've seen a fence before, but in this case, it's an electric fence, so it's usually like a white tape. So they actually haven't seen this specific fence before. So they see it, and they walk up to it. They touch that fence, and of course what's going to happen is they're going to get an electrical shock from that fence. They then feel that, and of course, they'll react to it. It's not pleasant, and they'll usually do something like turn around or run away from it. And then they're able to make this association. So next time they see that bright white strip of tape across their paddock, they know not to touch it because it's not going to end very nicely for them. So that's called associative learning. They're associating something they can see with an outcome which they then can use their own choice to avoid in future. So how many of you have ever heard of clicker training? So like for dogs, clicker training? Yep. So this kind of works on a similar concept as clicker training, because clicker training, what you do, it's just a sound that you use. Dogs have never heard a click before from a clicker, so they have no idea what it is. But as soon as you press that click, you give them a food reward straight away. And you do that enough times, and eventually your dog will understand that sound means food. And then you use this with other behaviours, so then you can actually train your dog really, really easy. If you haven't used it before, I highly recommend, because it's an amazing way to teach them. So this kind of works the same way. So the sheep approaches, or the cow approaches this boundary you've set up with a GPS, and they hear this sound. I've actually got an example. I don't know how this is going to work, holding a microphone. But in the case for sheep, it sounds like this. So that's the sound they hear when they approach a fence. So much like a clicker, they actually have no idea what that is because they've never heard it before in their life. So they keep walking. They have absolutely no response to this. When they keep walking, this sound goes for like 2.5 seconds, 2 seconds for us when we're training sheep. I believe the cattle collars are 2.5. If they keep walking, they then eventually hit the fence. So they get an electrical stimulus. And of course, much like the electric fence, they're going to have a response to it. In this case, the same thing, they're going to turn around and run away. But then with enough interactions with this, much like the clicker training, do it often enough, they're going to learn what that sound means. So they know in future not to go near that. So they hear that sound again, they're going to do the right thing. And that's associative learning. But like clicker training, it's a little bit smarter than that. Because once they've made that association of that sound, we then incorporate specific behaviours that the animal do, so then they can learn how to interact with this fence properly. And this is what the cattle collar does. So here's an example of that smart behaviour that it incorporates. So here is the GPS line that we've set up with the fence. So the fence is there. The cow's on the inside of the boundary that we're trying to keep them out of. So if a cow walks up to that fence and lies down and does nothing, then nothing happens to it. It can just lie next to it like it can lie next to a normal fence. If it runs through this fence, nothing happens to it again. Can anyone think of any reasons why you don't want to be implementing on a fence on a cow or a sheep that's running? Can anyone think of any reasons why you don't want to be fencing them in? Because they'll keep running? Yeah. I mean, they'll keep running, but why don't you want to put a fence in front of them when they're running? So I heard someone say dogs. So for sheep, you don't want them to be making a choice between a fence that's going to give them an electric shock or wild dogs that are chasing them. Or another example could be fires. So when there's a fire up, it's quite hard for livestock to get through fences. So you don't want to be shocking an animal or giving an animal a thing that they have to face when there's something else going wrong. So it's giving them this choice of avoiding something that's going to be a lot worse. So it doesn't give them an electrical stimulus when they run. But once they calm down and stop walking, it'll put the fence in front of them again and actually slowly bring them back to the rest of the herd. So if somehow the cow or the sheep finds itself on the wrong side of the fence, but it's facing the right way, so it's walking back into the area it's supposed to be, this thing doesn't give them an electrical stimulus either. So it lets the animal do the right thing. And then, of course, at the bottom here, if a sheep or cow is just calmly walking through or towards the fence, it hears the sound, it chooses to ignore it, then the fence comes into play and acts just like a normal electric fence. So this is just a video of what it looks like. So is that meant to just work on a click? So this was work done with CSIRO. So that's the cattle work that they did. So that red line is the GPS set fence line. And this was run for about 8 hours or something. So these cattle were nice and calmly kept on the right side of this virtual fence. So that's just an example of it working in cattle. But what about sheep? So I'm going to go into my territory because I really love my sheep, so I'm going to be talking about them. So how can we use virtual fencing for sheep? So like I showed, sadly I don't have anything fancy like the cattle automated GPS collars, and I have to do everything by hand at the moment. So I use a dog collar for now, so this is just to help us figure out proof of concept. So I played the sound before, so that's what the sheep hear, and we play that for 2 seconds, so then the sheep has enough time to react to the fence once they've learnt, and also gives them enough time to actually learn it. And we just use these nifty handheld devices that actually help us implement the audio cue that I showed, and also to implement the electrical stimulus. So, like I said, it's proof of concept stuff at the moment for sheep. So we know a lot about the cattle, and that stuff is close to commercialization, whereas with sheep, I have to begin from square one and answer all the questions. And the most important one was, using that associative learning, can we actually teach sheep what a virtual fence is and to actually react to it. So this is just an example of how we started that. We trained sheep on their own first. And that little rock boundary is our virtual fence. The sheep approached it, got an audio cue, and turned around just like we wanted it to. So that was a choice video, so it's a very well-trained sheep. So it's probably done this a few times already and built up that association so it knows what that audio cue is and it knows what to do when it gets that audio cue. So can anyone think of some practical applications for virtual fencing? So if you're a farmer, what would you use it for?
Cell grazing.
Yeah, cell grazing is a very good one because if you don't know what cell grazing is, it's used a lot for dairy cattle, for example. So they have small strips of paddock that they use for grazing, and they constantly have to put up temporary fences and then move them manually, which is, of course, a lot of labour for the farmer. So can you imagine having a nice virtual fence that you just set by a computer and change it in the morning and without going outside? What else would virtual fencing be great for? No ideas? Yes, yep. So one of the really exciting things about virtual fencing is allowing people to actually fence areas that are really hard to fence, such as sensitive ecological areas. So think of like a riverbank where it's really hard to put a fence up, or where it can often be swept away from floods and things like that. So it's a lot of effort to put up a permanent fence there when you know it's either going to get damaged or destroyed, or it's just going to interfere. So it's really useful for areas like that as well. So yeah, there's several practical applications that virtual fencing can be used for. I'll talk about a specific one that we've actually done an experiment for down in the south of New South Wales. So this is what it is. So in Mildura, they have really big cropping country down there. So when there was the drop in prices for sheep wool, most of the farms down there sold a lot of their sheep and pulled down a lot of their fences and just started going into cropping. And the interesting thing about a lot of the area, or a lot of the layout of the land here, is that the soil is really sandy. And these farmers have decided they wanted to bring sheep back into their farming system to just get extra money on the off season from their cropping. But there's an issue with this, with the sandy area. So it's sand and there's hills, and what sheep love to do is sit on the top of those sandy hills and just rest. And what ends up happening is they absolutely destroy the crap out of the top of these hills, and they just degrade the soil. So it just makes it a lot harder for farmers to then maintain that area for growing other things. So what we were trying to do was see if we could use virtual fencing to try and prevent this kind of issue. So what we did is we had this small section of a large paddock, so really large paddock. We made this small little fenced off paddock in the middle of this paddock. And at the top of this was one of those hills that sheep absolutely love to rest on. And we wanted to see if we could keep them off the top of that hill. So this is just a video. So that sheep up the front there just received an audio cue and turned around. And what's really interesting is if you watch him, 2 other sheep turn around with him. And then he goes back for more. So again, these sheep had access to this paddock for a while. So what we wanted to see was first, of course, confirm that they actually used the top of this sandy hill like we think they would. So we GPS tracked them for about 2 days. And then after that, we put a virtual fence up to stop them from going to the top of this paddock for 3 days. And then after that, we removed the fence and then watched them for another 2 days to see if they actually went back up the top of this paddock. So what we found out is by the 3rd day, all of these sheep actually learnt to respond to the audio cue, which is really important, as previously we had only done experiments in individuals. And of course, that's not really practical for a farmer to be training 1 sheep at a time to a virtual fence. So these sheep in the paddock managing to learn the virtual fence within a group was a really important question that was answered. And also, we found that, the other important thing, so the point of putting the fence down and letting the sheep have access to the top of the paddock again is to actually confirm that the sheep learnt to respond to the audio and there wasn't like a visual cue along that fence line that told them there was a fence there. 'Cause sheep are very visual learners, so if there was something obvious there, like a tree or something, they could have associated those electrical stimulus that they got with the tree that was there. But what we found out was that, well, first off, this is the base thing that I said we did. So we tracked their movements along the paddock. And of course, like we expected, they really loved the top of that sandy hill. So then we put up the virtual fence, which was really effective at keeping the sheep off the top of that sandy hill for the 3 days that they had it up. And then, of course, most importantly, is once we took it down, the sheep were really happy to go back over that fence. So that's a good indication that the sheep were learning to respond to the audio cue and not a visual, like, anything visually giving them a cue that there was a fence there. So this is one of the most important things for virtual fencing, because if you want to be able to use strip grazing, then you want to know that the sheep or the cattle are going to actually cross over where the old fence was. So we know that's what they're doing and that they're learning it is the audio cue that's indicating there's a fence there. So future applications for virtual fencing. We kind of talked about some of them. So the practical applications of being able to actually fence off delicate areas within paddocks and to block off cattle and sheep from getting to lakes and rivers and things like that, and protect those environmentally sensitive areas, as well as preventing sheep from going on top of those sandy hills and absolutely destroying them. So there's a lot of future applications that farmers have thought of, and other things they have considered, because these things have GPS. I've been asked things like, oh, can you be able to figure out if your sheep's not feeling well or something, because the GPS will give you some kind of information, like your sheep's been sitting there for 6 hours and doing nothing, maybe you should check it. And because it's GPS, they can actually do that. And I know another interesting idea I had from a farmer was whether you could use it to figure out whether there was a dog attack going on. So I know work done by UNE has actually shown there's a specific, well, there's an algorithm that can figure out dog attacks, because when sheep are getting chased by dogs, they actually run in a certain pattern that they don't normally walk or run in. So these things could potentially be incorporated into this kind of technology to then provide warning systems to tell the farmer, oh, hey, there's some suspicious activity going on in this paddock with your sheep. Maybe you should check it out. So the future's looking pretty bright with technology for farmers and for virtual fencing. And of course, this is a ginormous project. So it works across cattle, dairy cows, as well as sheep. So I just wanted to thank everyone that helps with these projects, especially the technicians and working with our manual collars, because they're really long days. So yeah, thank you guys.
Thank you, Danila. All right, it's time to hear from our second speaker, Dr. Will Billingsley. Dr. Billingsley graduated with his PhD from Cambridge University in interfacing people with machines. He's now a senior lecturer in computational science at the University of New England. Let's hear it.
Thank you. All right, so, oh, break. That was your break. Sorry, that's me. Now, I should first of all apologise that, of course, this is the future of farming, and following from a fantastic talk on the future of farming, we've got an absolute city boy who can just about tell the difference between a sheep and a cow. So what I'm going to talk about, it's kind of the light relief to follow the serious science that we've had, as we'll see. Now, as a robot thinketh, there is a verse out of Proverbs, ages and ages ago, of course. For as he thinketh in his heart, so is he. And this is kind of suggesting that, you know, you are what you think, if you like. And it became part of a self-help book by someone called James Allen, As a Man Thinketh, that was trying to encourage you to, if you like, have good thoughts and attitudes in life, because that will attract success. And the thing I was thinking is, well, in the case of artificial intelligence, in the case of robots, we create how they think. And so, you know, if a robot is as it thinks and we create it, that is my segue into, if you like, what do we want the machines, the intelligent machines that we build to be like? What sorts of attitudes do we want them to have? Now, who's heard of, you know, Elon Musk and Stephen Hawking and various others have occasionally talked about their fears of artificial intelligence taking over the world? My fear is a little more mundane than that, and it is possibly because I teach software engineering and human-computer interaction. And so my fear for the future of AI is probably best summed up by a character out of Little Britain. So in Little Britain, David Walliams has this character where he's cross-dressing, and his character sits behind a computer, and someone comes in and asks them at great length something perfectly reasonable, and they discuss it, and then his character goes, types in the keyboard and goes, computer says no. And so he said, well, but could you perhaps, and goes on in some other perfectly reasonable thing. Computer says no. And I mean, this is, you know, one of those things that as an HCI person is so totally frustrating. All right, it says no, but why? Why is it saying no? How can I do the get to yes? Sorry, I'm leaning on all the self-help books for some of my segues here. And this is slightly my fear for the future of AI, or at least one of the things I would like to ensure that we avoid. And the reason for this is as the machines get smarter, they can do more for us, but they become harder for us to reason about. So this is, the writing on that's a little bit blurry. Many apologies for my cartoonish scribbles that in here are probably a little bit difficult to read. One of the things you kind of teach in user experience design and interaction design is that, okay, you've designed some fabulous piece of technology, and you've put it out to the user, and you've said lots of things that are about it, the advertising, the documentation if there is any, etc. And then it's in your user's hands. And your user has to build up a mental model of how this thing works. What's going to happen when I push this button? And that mental model, if you can imagine the thing getting smarter and smarter and smarter, well, does that mean that our mental model of how it works has to get smarter and smarter and smarter? So I'm slightly jumping to the punchline here of what I'm going to talk about. Because this is, if you like, one of my worries, is that suddenly the AI will get smart enough that it becomes hard to reason about. And so my challenge, which I'm going to tell you right now, I don't entirely know how to answer, but this is kind of one of the questions I ponder at night, is how do we make machines reasonable as well as clever, so that we can make these smart machines, but we have a good idea of what they're doing and how to work with them. Now, that was kind of, if you like, foreshadowing where I'm going to get to at the end. But first of all, I should do the formal introduction. So my name is Will, and I'm a computer scientist. And if that sounds a little bit like I'm at a support group admitting to a terrible lifelong addiction, I apologize, but it's slightly intended to convey that for me, this computing has been something of a lifelong compulsion, and I blame my parents for it. Because, well, my father was a professor of mechatronics, robots, and so I grew up with robots around the house. This is a poster for a conference in 1981. I was a little bit too young for this one. I picked this poster because my mum designed the poster. So my father's a professor of robots. My mum's a graphic designer, so I'm going to get kind of interested in creative things about technology. But this competition was back in kind of the earlier days of robotics, and you had a little robot with a microprocessor on it, and you put it in a maze, and it had to solve the maze, a bit like a mouse solving a maze, hence micromouse. And occasionally when I was a kid, I used to get asked to go along and do the timing for these things, and I'd talk to the people that designed them, and the artificial intelligence for how they solved the maze. And so this was sort of the sorts of things that I was growing up with. And I also had an older brother, and my brother was 7 years older than me. And like many younger brothers, I was a little bit competitive. And he was really into maths. And so the way I learnt to program was by writing artificial intelligence backgammon, basically a backgammon player to play against my brother's backgammon player. And he usually won, but that was kind of okay because he was 17 and I was 11, so I could kind of take the honorable defeat, if you like. So inevitably, I grew up and I headed off to do engineering at university. Now, this is the Pint of Science, and I've stuck a thing up about engineering. And it's because I want to borrow a terrible joke, well, not actually quite a good joke of my dad's, which is about the difference between science and engineering. Who knows what the difference between science and engineering is? So the way my father would put it was, you know, I say, what's the difference between science and engineering? Well, if they put a man on Mars, it will be heralded as a great achievement for science. And if the rocket blows up on the way, they'll put it down to engineering failure. The scientists have the advantage of, you know, they find hypotheses and they prove themselves wrong occasionally, whereas the engineer's got to get it right. So I went off to, well, our task is to make the world a better place for you. So I went off to university and I did this. And afterwards, I worked for a company in Brisbane that did software. Not many people will have heard of it because all their customers are businesses, but they do the billing and the customer care system for Virgin Mobile, the German Railway Network, and various other places. And I used to get called Bill when I was younger. And so I'd gone along to this place that did billing systems and customer care systems. And so there was an unfortunate danger of my being Bill Billingsley of billing systems. But fortunately, they had mercy on me and put me on the customer care system. But after a while, I discovered, if you like, that the interesting thing with computing isn't really in writing the code. It's in what on earth should this thing do in the first place. And the chance came up to go and do a PhD in the UK. And the project I joined was one, it was the intelligent book. What if we had textbooks that were smart, that understood what they were teaching, that could learn from their interactions with their students, etc. This was some years ago. Educational technology's come along a little way. And when I looked at this, I thought, this is kind of interesting, because textbooks, and this is Hodder's arithmetic from 1667, something like that. For 350 years, textbooks have been one of the main ways of conveying knowledge and educating people about things. And there's some aspects I really like about them. The aspects that I most like about textbooks is they don't complain when you don't read them. There's a wonderful, sense in which I've never been marked down by a textbook. I've never had a textbook complain that I went to a different textbook, if you like. And though this sounds kind of facile and obvious, the educational technology that I was seeing around at the time wasn't entirely like that. There was an awful lot of it that was very much more being your teacher, being your master. And it would do things like it would have a very complex model of the domain that it was modeling. And every time you did something, it would use Bayesian inference to work out the likelihood that you knew any particular factoid or thing that you were supposed to do in solving the problem. They call it model tracing. And I wasn't totally satisfied about this because I quite liked this aspect of textbooks that, if you like, they are your servants. And I was, how can we design smart technology that nonetheless you are most definitely in charge and there is no two ways about it? To start with, we looked at a problem in electronics. And so there was a piece of AI called a constraint propagator that could solve these problems but would produce solutions that were a mile long. And so the first thing we did was we decided, okay, well, the way we're going to the way we're going to make this more accessible for starters is we're going to get the student to be working on a diagram, the sort of thing that they have to write on an exam. So instead of getting the students to work in the programmer's language, we bring the program to them. And what if the AI was your partner instead of your marker? And then it could animate explanations on the diagram and all sorts of things as you went along. And that all worked quite well. And so we thought, great, we're going places with this. And we then decided to try and do something like this for discrete mathematics. Discrete mathematics is, well, some of it is all about proving things. And so there is an equation about, for all m greater than 0, here is some condition on n, and we want to show that this holds for the Fibonacci sequence, some particular sequence of numbers. Possibly unsurprisingly, given the slide I've just shown, this was the subject that students both complained about most at university and found hardest at university. So we wanted to see what we could do to solve it. And just round the corner from the HCI research group was the automated theorem proving group that would build machine reasoning systems that could solve these kinds of problems, the kind of reasoning systems that, for instance, were used in solving complex things like Fermat's last theorem, etc. Now, when I was talking about this and how we wanted to get students using them, the first thing they said was, oh gosh, no, that's a terrible idea. These proof systems, they're almost like programming. If you can't prove something on paper, you've no chance with the help of a proof assistant. And so at the one hand, I was like, ooh, okay, makes the word assistant kind of interesting. On the other hand, as a PhD student, I thought, fantastic. Loads of people have tried this. They found it totally hard and impossible. That means I don't have to get very far with it, and they'll give me a PhD for getting somewhere. Sorry, a certain amount of PhD student cynicism. But so the way we went around this, first of all, we wanted to bring it a little bit closer to how students work, as we came up with this tile-based way of doing mathematics that's a little bit like, so in schools now, a lot of children get taught programming through a thing called Scratch, which is very similar to dragging tiles around. This was before Scratch, and I really should have done it for programming, and then I might be as famous as Scratch, but I didn't. But this would let you construct the proof in a way that would look a bit closer to how it would on paper, just by dragging bits about and playing around and scattering bits all over the place. And it kind of worked, and we could get students using this proof assistant having watched a few minutes of video instead of needing to have, taken about 6 months to come up to speed with the proof assistant natively. But there were some problems with it. One of them, was that there is something they don't tell you about proofs, is what lines you have to write down and what lines you don't. Proofs, if you were to put down all of the rules you're applying, would be phenomenally long. And so there's the question, which ones do you have to write down? Which ones don't you have to write down? Because if there wasn't something about that, then you could just start with the proposition and end QED. Because, well, it does flow from the proposition, and so, theoretically that's true. But we want you to show how it's true. So I watched about 13 hours of students doing mathematics with human tutors. And the short answer was, people don't know how to do this either. It works out that if you've got a human tutor there, the way it works in terms of what lines of proof you have to do is the student will get it wrong for whatever wrong is. The tutor will say, oh, I think you've missed a line out there. And the student, seemingly not wanting to be embarrassed by not knowing, not questioning whether they should do this, will go, oh, I'm terribly sorry, and write it in. And so you completely gloss over the question of, well, which ones do you and don't you have to write down, and how do you tell? So when we were doing this, we had the same problem. How do you put down the rules that you don't have to say? So for instance, A plus B equals B plus A. So if I swap two things around a plus, I shouldn't really need to mention it. And proof assistants have something called a simplifier. So we thought, well, what we're going to do is we're going to say that you don't have to state any rule that's in the simplifier. And then we had a look at it and discovered that there's 1,500 rules in the simplifier. And you just can't say, the following 1,500 rules are considered trivial, and you don't have to mention them, because it's just impossible to, to do that. So then we thought, well, okay, we're going to have to show you the rules that you do have to use. And that's going to give you a prompt as to how to solve it. And that's going to break our wonderful ideas that this is just thinking with you and able to cope with the unexpected answer. And then from my 13 hours of watching students doing maths on the board, I kind of recalled that people are terrible at that too. And on the occasions when a student came up with an unexpected answer, every single time, what the tutor did was they'd go, that's interesting. Well, what we expected you to do was, and they'd kind of launch into this potted answer that they'd got in mind. And it's kind of inevitable, because we don't set questions just for the beauty of setting questions. We set them because we kind of got a point in what you're after in the answer. And so I then decided, well, having done this and made the sort of mite of progress that I thought would ensure that I got a PhD, I thought, well, what would you actually want to do? And this is artificial stupidity. Roughly speaking, what if we made the tutor, so dumb that you can't help but know what it's doing? And it also turned out to be useful because most most exercises, even in discrete maths, aren't set in symbolic logic. They're written in English. Albeit kind of that peculiar kind of English that starts, let D be a collection of disks in the plane, etc. I'm going to move off that slide before you try to read it. And so we came up with something that still looks a bit complicated, but behind the scenes, it's not got much of an idea of what any of these statements are, the reals of the union of the rationals and the irrationals, etc. That's just text. Behind the scenes, it just knows how you need to construct this proof, and using predicate logic instead of number theory. And so because of this, it means that it's a lot more able to, for the student to reason about it. And that is important when things get stuck. Because the other thing that would happen in the number theory proofs was the proof assistant would get into this state where it would go, I don't know that you're right, but I can't show that you're wrong. And then the student's going to go work out, well, what do I do now? How do I get you into a state where you can actually give me some help? And that was where we were having this problem of it being too smart and it being a usability issue. So we tried this, and this was, starting to bring it a step towards human language. Now, meanwhile, I am a terrible underachiever compared to my peers there. So down the corridor from me was the guy that founded the Raspberry Pi project. Around next door to me on one side was a chap who's now sold one of his startups to LinkedIn for $15 million and started another. And on the other side next door to me was a PhD student who was working on how you get computers to understand human expressions, because we already have an interface. We talk to each other. That's how we communicate. We show things with our faces, etc. How could you get a computer to understand when you are screaming mad at it and scowling it down the barrel of its camera? And so Ranarel Kaloubi, she did this software that it tracks points on your face, so that first of all it can detect facial gestures, like an eyebrow raise versus an eyebrow flash, where the eyebrow goes up and comes down again. And then based on how the points on your face are moving, the gestures you're making, the combination of gestures, it can use a Bayesian network to work out, well, this is what I think you're trying to express. So if I tilt my head and I raise my eyebrows, I might be looking interested. And if I tilt my head and I furrow my brow, I might be looking a little bit uncertain about what you're saying. Many of you are giving me that expression right now. Anyway, this was during her PhD, and this is now a company in the US, Affectiva, that is doing all sorts of things from detecting what parts of adverts people are interested in to whether a driver is getting tired or confused, stressed out in the car, driver monitoring, etc. Later on, so this is from the products that you can download this on your phone, Affectiva. And later on, they started to apply something called deep learning to it. And this is my clumsy segue into something about deep learning. So deep learning suddenly became a bit of a rage when a company called DeepMind, that's been bought by Google, got a neural network with several layers and taught it to play video games. So they taught it to play these Atari games, not Call of Duty on the PlayStation, but Atari games because they're lower resolution and you can put this into a network. And they managed, without if you like, writing any strategies into it to get the network to learn to play many of these games better than people can. And my COD introduction to what goes on in a neural network is you have these layer of neurons at various different points, and each node in one layer is connected somehow to all of the nodes in the previous layer. And it is a combination, a function of the values in those previous nodes. And the next one, each node, is a function of the values in the previous nodes. And you get about 7 layers of this, and what it can work out can get quite complicated. And what you do is you just stick the raw data in on the left, and on the right, you want there to be signals that might be something like, there's a dog in this picture. And then the clever part comes in the training algorithms that you apply that says, well, okay, I've shown you lots of pictures of dogs, and you're not telling me very much here, but I would like to correct you based on lots of examples. You said there was no dog. There is a dog. Please update the weights in your graph as follows. And they are stunningly effective, and they are the natural language processing that lets you go, hey, Siri, or hey, Google, tell me what time the shop's open to tonight. And they can do image recognition, voice recognition, you name it. And for me, as a computer scientist, someone who teaches students, they pose a little bit of a problem, because this thing learns really, really well. But it's a massive grid of numbers in an architecture. How do I know what this thing is really learning? And how do you teach that? How do you relate to this thing that is just a grid of weights in a very, very complicated network? One of the things they came up with was, well, what if we go the other way around? What if once we've trained this network to recognize dogs, we give it a blank image and say, please alter the pixels in the image to maximize the value of the dog neuron, to maximize the dogginess you see. And doing that, they could generate pictures of what the network thought these things looked like. And they kind of don't quite look the same. So banana, you can kind of see bananas in there in different orientations as it's learned to recognize different orientations of banana. But they sort of look a little bit like abstract art. And then the next kind of thing comes up, which is that, all right, so for an engineer, the mental model that you've got of what's going on in there is quite difficult. For people, it turns out to be a little easier. So one of the things you can do is you can train it on a particular style of image. So suppose I trained it on loads and loads of episodes of The Simpsons. This is what drawings of The Simpsons look like. And then I give it a picture, say, there's me talking to Ewan, and I say, all right, now I want you to evolve this picture so it looks more like The Simpsons. And that's something we can relate to quite easily, and it can do that pretty easily. But from the engineer, the software engineer's perspective, it's like, yeah, but what did it do? If you know what I mean. So this kind of started to raise these questions about how we think about this kind of computation when we're starting to get these sorts of deeper AI going on. One of the ones that we did, student Mark McKenzie, we were looking at this, and I had kind of this interesting thought of, well, if these are artificially intelligent, if they can learn things, is there such a thing as artificial pedagogy, how you should teach these things? How do they behave? And that kind of reminded me of one of those material diagrams you see of like grains in a piece of metal. And I wondered what happened if you bend it one way and bend it back again. Teach it one thing, then try and teach it something else. Does it forget what it's learned, or does it kind of learn to abstract over the example? So what if we tried to teach it multiple games at once? And so, does it just become a tangled mess, or does it bend back neatly again? So we tried training one of these deep networks on 2 Atari games at once, and actually interleaved them rather than doing one followed by the other one. So we didn't quite get the bend it and bend it back again. But we started to find that there were things that you could discover about this. So for instance, if you do another visualization to show the state space of the different games, you can discover that, for instance, for one game it has really short-term rewards, whereas another game has long-term rewards, and the short-term rewards just win, and it just learns the short-term rewards and forgets about the other game entirely. You can get other ones where actually this game's too complicated for the number of neurons in the network when it has to remember this other simpler game as well, and so it does really badly on the more complicated one. And you get other ones where it actually starts to learn strategies in both of them. There's, I think, boxing and centipede both work, that if you head to the bottom right-hand corner, you can then just hammer the fire button and win. And so this was kind of interesting in terms of, okay, starting to come up with ways that we can think about how these things behave. The next one I want to head to, though, a lot of the stuff I do is still on education technology and teaching students. And there's been all this push on learn to code, hour of code, students everywhere learning to code. But they're learning the kind of code that looks like this, where we're doing it instructions after each other, and we're teaching them, okay, actually code is a language for engineers so we can understand it. The one the computer sees is the compiled stuff that gets executed in the chip and is even more unreadable. But nonetheless, it's kind of this sort of building things up code. And so we've got ways that we can teach that. So this was, we decided to do kind of a lecture for 5- and 6-year-olds from TAS a couple of years ago. And so this is a modified version of Angry Birds. Well, sorry, not a modified version. It's designed to look a bit like Angry Birds with my son's drawings of the Angry Birds, with just 3 lines of code exposed, because 5 and 6, they're not going to be reading a whole heap. They can read, but not a huge amount. And they started to get this really well. So they started to ask questions like, all right, can you launch the thing into space? Set it to 1 million. And they asked me to do things like, all right, what's it like on the moon? Set gravity to what it is on the moon. And you'd see the birds slowly floating around as if they're on the moon. And for me, that was brilliant because they'd got this idea that the code was relating to what was going on. They'd got the idea that in code you can do things that are impossible in the real world. We couldn't really try Angry Birds on the moon. But then, okay, what if we're entering this world, though, where what we're doing for more and more things is training deep learning networks, and we're staging bits of machine learning together instead of handcrafting algorithms? And so another student, Clinton, we made a little robot that has a mobile phone on the front of it, so that we can drop different algorithms as apps onto the phone, and you control it from another mobile phone in your hand. And so the idea is that you would be programming this robot. And we did it in the traditional way, but we thought, well, okay, can we teach people higher level concepts about how you design, self-driving cars or anything like this without teaching the lines of code? And so we'd do things like, well, what if instead it was spotting the commands like road signs in the environment? And so you'd, the game that we actually came up with it was you had to shepherd the robot into a box by holding these commands that said right, move, left, etc. in front of it. And then you'd kind of unpack, well, okay, what was it having to do along the way? It was having to spot the words, it was having to do optical character recognition, then it was having to interpret that and then relate that into commands, etc. And trying to get those higher level concepts around what goes on in the machine without writing the actual lines of code themselves. And the next one we did after that, just because I like playing with my friend's stuff, really, this is my dog. This is my dog, Rosie. And you can't really see it very well, but the thing that is in her mouth is probably her favorite item in the world, which is a sock. She is the world's most notorious sock thief. And, well, the way I program my dog isn't that I write instructions and hit compile. I program my dog like that. Leave it, Rosie, etc. Well, what if we tried teaching the robot like it was a dog? And so we had, the Rosie bot, if you like, that wants to go for the sock when it can, and you have to tell it not to. And so you would teach it not to by scowling into the other phone. And so, we can apply the Affectiva API on the mobile phone to spot that you're scowling and start getting it to learn not to go near the dog. And then, again, you unpack it in terms of, okay, what's it having to do in all of this? Track the movements, work out the gestures, associate that with the behavior of the robot, etc. And so this is, if you like, the space that I'm kind of up to at the moment. And I did say that I was not quite going to solve this problem, but in terms of what are the mental models that we have. The place I thought I'd finish up, because I am sure I'm running over time. I'm positive I'm running over time. Earlier, ooh, this is working. Hang on. Let me just pause that for a moment. I need to set that playing in just a moment. So, earlier this month, Google announced at their developer conference something called Google Duplex. So normally when you do things with the Google Assistant or with Siri, etc., you can tell it to look something up and it can search something on the web. They realized that there's lots of things you do, like booking hair appointments, where you actually phone the store. And so one of their innovations recently is that you tell the Google Assistant what you want, and if it needs to make a phone call to do it, it will. At the back end, it telephones the store, and they had this amazing demo where the Google Assistant phoned up the shop and said, apologies for my terrible accent here, hello, I need to book a hair appointment for a client. Something around 12, have you got anything? And the assistant at the other end would go, oh, let me just look that up. And the Google Assistant, the AI, would go, and fill in the gaps. And it would even insert the ums and ahs, etc., and try and behave in a more human manner, understanding us and talking our language, if you like. Now, on the one hand, everyone was fabulously impressed, the way they are with tech demos. On the other hand, within, I think it was about 5 days, the video that is a spoof that I'm about to show you came out, and I should say I did not produce this. This is pilfered off YouTube, and I have forgotten the name of the person that did it. And so this is a fake Google Assistant, Google Duplex call.
Hello? Hi, can I talk to Diane, please?
Speaking.
Hi, Diane. I'm calling on behalf of John to schedule an appointment.
For what?
The appointment for you to come pick up your belongings from John's apartment.
Excuse me?
John would like you to remove your belongings from his apartment.
What are you talking about?
I'm very sorry, but John has decided to end your relationship.
Is this a joke? Put John on the phone.
I'm sorry, John's not currently available.
What? Where is John? I cannot believe this. This is bullshit.
How does 10 a.m. sound?
Are you fucking kidding me?
Oh, if 10 a.m. is not available, what time is suitable for you?
Fuck you! Hello?
Hi, can I talk to Diane, please?
Okay. Yes, sorry, there we go. Adam Fireman, the leaked demo of Google Duplex. But so hopefully, I mean, the Google Duplex thing, that is this deep learning stuff going on. But it kind of, raises kind of these kind of issues of how much do we actually trust these things, and that trust as our mental model of what it's going to do. How can we understand what this Google Duplex thing is going to do in the call that we're not hearing when it is masses of AI running on Google servers? And so that is, if you like, the unsolved problem that I would kind of like to solve, but I don't really expect to actually solve it. Thank you.
All right, well, I hope you've been paying attention. I do like the way in that video that the written expressions had lots of asterisks covering parts that people might find offensive, but the verbal didn't seem to follow suit there. Maybe that's an AI issue we can look into a bit later on. All right, this is the part where you get to ask some questions. I've got some questions, but before I get started on my questions, I just thought I'd ask, does anyone in the audience have any questions for any of our speakers tonight? Put your hand up, we'll get a microphone to you, spotlight on you, broadcast around the world. No? Oh, yes, please.
Sorry, I forgot your name, pink-haired lady.
Oh.
That's all right.
Excellent.
So I had a question. So you know how when you were setting up those with the sheep, with the virtual fences, you aimed not to put a visual stimuli there because you wanted to know if they responded to the auditory rather than the visual. But would it be worth, because obviously farmers might place these in places where sheep might have visual stimuli, so would it be worth doing a test where you have very notable visual stimuli with the fence and then take it away and see if they still go past it?
Yeah, it would be a good idea to do something like that. So we, because previous experiments have been done that's shown like having the additional like visual cue can actually help the learning with the pairing of the audio. And we did find we had in an earlier experiment when we trained them on their own, so they had a very visual cue, which was a food trough in the middle of the paddock, which they were taught to walk towards. And then what we did is put a barrier around it after they learnt there's food in there. And so that's a very strong visual thing that they had. And when we were then training them to the virtual fence, they had to walk towards this food trough again and learnt the audio cue and the electrical stimulus that way. But what we found was they really quickly learnt to just not approach that food trough because they knew that was like kind of linked to what was causing them to get the electrical stimulus. So that kind of indicates that that visual thing there was a really strong or easy way for them to learn. And there was a lot of variation in the animals that learnt to respond to the audio cue even when they were just approaching this food trough. So what we ended up doing was picking those animals that we had thought learnt to respond to the audio cue, and we put them in a completely different situation that didn't have that visual cue anymore. And we found that even in that completely different situation, they still responded to the audio cue. So we've done something similar to that just through the actual experiments that we've done. So if that answers that.
Thanks. Anybody else got a question?
So with the floating farming, you were talking about pesticides coming from the farmers in those situations. Is that just the farmers using the pesticides incorrectly, or is that just generally from the farming itself? So even if they're using it correctly, would that contribute?
Actually, they use pesticides according to the instructions on the company instruction, but sometimes they use more than time according to the instruction, because at the time they face a lot of the pests and disease. At the time they use a lot, so I think it is the incorrect usage of the pesticides of the farmer. Yeah.
Okay, thank you.
Yeah.
Just a virtual question, fencing question this time around as well. So what is the accuracy of creating the fence boundary lines? Because with GPS, there is always a certain level of error associated. Yeah. Is there, you mentioned there was the base stations transmitting where the fencing was. Do they act as a differential GPS, or is that unrelated?
Ooh, I don't exactly know how the base station works in terms of the collars, besides actually just relaying the information from the program to set up the fence, and then relaying that information to the collar. As for the GPS, yes, it has that like sway in like where the actual fence is. So for most GPS, it's like 1 metre or 2, I believe it's for that one. So it's a few metres on either side of where you actually set the GPS line is where the fence could be, depending on that GPS sway. So it does experience that, but yeah, it's just a few metres.
So not significant enough to cause any issues?
No, so it won't be something like kilometres. If it's only a few metres, it's not going to be so much of an issue. Yeah.
Any other questions? All right, I might fire a few off then. Oh. I can't see where they are.
I have a question for Min. This is, I guess, a basic biology question, but the dung beetles, how long do they live for and how far do they travel? Like when there's no poo in an area, or across seasons, where are they? Do they die off, or do eggs or larvae lay dormant, or do you know that?
Oh, that's actually a very interesting question. Regarding that actually richness, there are many species, and the species are some are like annual and some are biennial and some are perennial. The diapers, that means sleeping, that depends on actually the species. And regarding flight also, some species can fly a bit like just 50 meters in 1 year, and some are very good flyers, they can fly a bit longer distance. So regarding that sleeping also, some are mostly are actually that is like larval or adult diapers that may happen, depending on the species actually. There is no actually particular species, we have to go for that particular species. What do they do, yeah. I have no exact idea, but in general that is, yeah. There is lots of diversity regarding that.
Yeah. Okay, thank you.
Thank you.
Right, I'm going to have a good look around this time. Aha.
So another question for Danella with the virtual fencing. So following foot and mouth in the UK in the early 2000s, one of the problems was the widespread, well, the total culling of some sheep flocks. And one of the costs of that was the generational knowledge that the sheep had, particularly on the hill farms. So for those who aren't familiar with hill farming in the UK, they're put up above the fence line and left on the hills, and then only brought back down in lambing. Is there a way that virtual fencing could be used to rebuild that knowledge for the sheep flocks? They generally knew where their home farm was.
Yep. Oh, that'd be an interesting one. I guess it could be a possibility. So I know one of the things they're aiming to use with virtual fencing. So if you notice for the cattle one, they actually call it an e-shepherd because it does more than just fencing. And one of the aims is to actually use it as a herding tool. So there is the possibility to be able to do that. So I guess you'd have to start by taking your sheep to the top of the hill and then using something like virtual fencing, you could slowly bring them back down. And then I guess over the years they would hopefully learn that pattern of movement, as sheep are quite, if you ever watch them in a paddock, they have a routine that they do. So I wouldn't be surprised if they would hopefully learn that pattern each year.
And then just follow it like sheep, I guess. Any other questions? I'm double checking. All right, I wonder if I can ask Mavroz a question. The research that you're doing, you mentioned, we're looking for more resilient rice for climate change, but what about for things like growing population? I mean, is the application for what your research is wider?
Well, the resilient variety, I was told to give my presentation in 5 minutes, so I couldn't talk in detail. So I had another hypothesis that will deal with the resilient thing. So for example, all over the world, the night temperature is increasing. And increasing night temperature is very harmful for rice production. Why? It has been observed that when night temperature rises, there is less rice production. And rice also becomes chalky. Chalky rice means there is something whitish in the rice. So why is this happening? We reckon that auxin is doing something there, because starch is produced by some genes, and those genes are controlled by auxin. And for the wider applications, yes, that might be, but currently I'm concentrating on these two hypotheses. And if I can have some finding, I think that will be really great.
Okay, thank you. Will these trusty AI computer thingies that all the kids are talking about, but seriously, how do we know that AI is going to look at data sets or information and interpret it in such a way that humans do? I mean, how much of the decisions that we make when we interpret information is human nature versus AI? How will they come to the same conclusions?
So the short answer is that they don't. What they do is inevitably going to be somewhat different in lots of different ways. I mean, the normal ones that we write, where we write particular algorithms, the handcrafted ones, clearly they're going to be different. The neural networks, even though they're biologically inspired, They are a very much simplified version of what goes on in your head. You've got cognitive architecture, you've got bits of your brain that are specialized for vision and for sound and for, you've got part of the back of your brain that picks up the reflex movement so that cricketers can hit the ball even though it's coming faster than you could consciously react to. Most of these neural networks, they're not quite like that yet. But they also have other properties, like they've got an awful lot more short-term memory than we have. We remember about 7 things, and they make fewer of the kinds of mistakes that we make, for instance. So the short answer is that we try and find analogous ways in which we can relate to them, and in which we can have models of, oh yeah, I can kind of see what it's doing there. It spotted something about that style and applied it to this image. But what it's actually doing almost certainly isn't what we're doing. There was one where they did a paper that was incredibly cited, where what they decided to do was see how they could fool one of these image recognition things. And so they trained a recurrent neural network to recognize things like American school buses. And then they decided to play it backwards and find out what the canonical American school bus looked like to it. And they got a thing that just looked like yellow and black stripy lines. And to a human being, looked absolutely nothing like a school bus. But from the set it had, those were salient things that school buses had that the other pictures it's seen hadn't.
So even though it interprets the visual input differently, or the interpretation of the visual input into a graphical output, it's still saying it's a school bus.
So in that case, I mean, it's saying it's a school bus, which basically means that the neuron that was trained for this going off represent school bus went off. We have layered the meaning on top of it, if you know what I mean.
Okay, thanks for that. Danila, you mentioned that you don't want the livestock to be, penalised for, running from disaster, for example, a fire.
Yep.
But what about if they're just spooked by something, innocuous or not nefarious, and start doing a dash for the mountains? What happens there? Does the farmer lose the herd?
So the way the cattle collars work, the GPS, so it has a smart algorithm in it. So it will just let them run, even if it's just something that spooked them. So they'll be able to run, and what it does is it waits for them to calm down and stop, and once it does that, it then puts the fence in front of them. So this fence will just continuously follow this animal. So once they've calmed down and stopped, and they try to walk forward again away from the area they're meant to be contained in, the fence is already there in front of them, and we'll just implement it all over again. So it just restarts again, basically.
And does the collar that they're wearing, etc., understand that it's running, and so therefore it, makes it deleterious? It doesn't.
Yeah. So because it uses GPS can actually be used to track how fast something is going. So it knows the average speed that a cow walks at, and it'll know when it's not walking at that speed just by using the GPS.
Thank you. Min, I'm interested that your research says that the dung beetles prefer sheep poo. Very interesting. If ever I'm having a dinner party, I will make sure it's on the menu. But seriously, what's the commercial application of that? Why do we care so much?
Actually, that regarding that choice of my treatments, I have selected those sheep poo and then cow and kangaroo poo based on some logic. That was sheep poo was based on population of sheep in Australia, then cattle also like that. And kangaroo because those were native, and the native dung beetles were supposed to be co-evolved with those kangaroo poo.
And they're breaking down the poo into good stuff that the soil can use.
Actually, the dung beetles, some like dwellers and some are rollers. They can roll, and for the roller species, there is ball already. The sheep poo is like plate-like. So they may be, that may be more easier for them to roll that because this is already a ball. So that may be, but I have to segregate my data because I have done this research just just attractant because most of the drive is based on smell. What the smell is, the beetles are attracted based on their especially smell, because some are specialized on some different type of poo. So in my opinion, for now, both native and introduced beetles are actually equally attracted to sheep poo. And that is actually important ecologically, because sheep poo may be alternative food for native dung beetles, so they can survive. Because in paddocks, in grassland, there are no more kangaroos or other small animals. So that poo can serve as a food for native dung beetles. It has some ecological implication. So we can still maintain the native dung beetles by the sheep poo. It has some other implication actually.
Okay, thank you. And Eamon, I wonder, you mentioned that the farmers, a high proportion of the farmers on the lake actually have a good understanding and good knowledge about what it is that these pesticides and herbicides and so forth are doing to the lake, yet they're continuing to do it. So what's behind that? What drives them year after year to do this to the crop?
Yes, actually, they know the effects of the harmful effects of the pesticides and herbicides, but they don't want to reduce the usage because they think that because their education level is low, so they think that if they reduce the usage of pesticides, their production may reduce. So they don't want to do this. So they have a high environmental awareness because they want to prevent their lake, because they are livelihood in this lake and they are dependent on this lake. But they don't want to reduce their pesticide uses.
So they're sort of conflicted between the long-term use of the river for farming and income and the short-term, we need the income now.
Yes.
Okay, thank you for that. Will, how big and powerful and whatever are these AI computers that we're talking about?
Ooh, tricky question to ask. I guess, I mean, this is one of those, how do you even scale that?
I have no idea, that's why I asked you.
Unfortunately, I've got no idea either. I mean, this is one of the problems. I go and do a talk on the things that I haven't solved, if you know what I mean. In terms of, I guess if I can skew your question terribly, if that's all right. You got all these people that used to talk, mostly science fiction writers and things, they would talk about the singularity as to when the combined power of artificial intelligence around the world networked together would become more than we can. I've always kind of seen that as more of a philosophical question, because, so terrible bit of philosophy, you stare at that couch and you see blue. Does the color blue that you're seeing actually exist outside your mind? Because actually what you're seeing is, you're seeing cells in your retina going off and signals going along, but now you're experiencing blue. And you've kind of got the same thing going on, that we read a certain amount of meaning into some of these AIs, but when it comes down to it, we're the ones building them. And just as we don't write computer programs usually for the sheer beauty of writing a computer program, we write them to do things for us. The same is true of all these AIs that we train. And so when you build the car to self-drive the car, sure enough, it can make a mistake where it didn't see the white van or it thought it was a false positive, and you can kind of have those things that happen through error or lack of thought. But kind of the idea of them thinking like us and being a bit like us sort of seems to me, I guess, a bit like trying to imagine the robot as teacher instead of the robot as servant. And actually, we usually design them to do things we want them to do.
Fair enough. Well, does anybody have any other questions? All right, please thank our panel. Pint of Science is a not-for-profit organisation that relies on the volunteer efforts of somebody's got a question, right? I'm going to the optometrist tomorrow.
Sorry about that. So I just have one question on the virtual fencing. Have we thought about, once it gets commercialised, what consumers of our food will actually think of it? Like, we're zapping animals repeatedly over their entire life. Has anything been done in that space to try and overcome that, or...?
Yeah, so that's like the work that a lot of us do up here at CSIRO. So we actually are looking at the long-term welfare, like repercussions of virtual fencing. So they've actually done experimental work and shown that the stimulus for the virtual fence in cattle is actually no different to them experiencing the stress of normal handling, such as going through a crush. So we know simple things like that, and we're still doing welfare measures on other things. So I guess one of the things to ensure good welfare is the fact that we base this smart algorithm on their behaviour, so we're not, you know, punishing them for positive behaviour or things that they do normally. So that's one thing that we do to ensure their welfare. Another thing is the virtual fence stimulus is a lot lower than electrical fence stimulus. So in terms for the sheep, it's something like, yeah, funny bone, like it feels like a really like fuzzy feeling. And then I guess finally is I think they're doing some work to compare like a virtual fence to an electric fence, because there's actually no like data or experiments done to see how quickly an animal actually learns an electric fence and what's the long-term repercussions of them like reacting or being near an electric fence. I don't know how many people know I've seen animals with electric fences, but even they will test those things even though they know they do like harm and things like that. So there still needs like work needs to be done in that space to see the long-term repercussions, but as far as we know for short-term repercussions, they learn the virtual fence really quickly, so it's something like 3 interactions for sheep, it's about 6 for cattle, so they learn what the fence is really quickly, so that's short-term good welfare outcomes. And yeah, for the cattle we know that their interaction with the fence is no different to just going through a cattle crush or a yard. So that's what we know so far.
Thank you.
Right, I'm asking and then I'm looking for a full minute. Are there any additional questions? In my defence, I actually can't see the back corner because of the light and the cameras, so I'm going with that. Are there definitely no questions? Over there, John Clay, you look like you've got a question. No? Okay. All right, I'm going to wrap up now. Please thank our panel again. Thank you very much.